we have an electron, which is moving with an initial velocity of 1.00 times 10 to the 6th meters per second in the I direction. It's going to pass through an electric field and a constant electric field of 25 newtons per coulomb. And so it's passing between two parallel plates. So we have, let's do this. If the electric field looks like this, which one is the positively charged plate and which one is the negatively charged plate? Miller.
The bottom one's positive and the top's negative.
Why is the bottom one positive and the top one negative?
Because the electric field goes from positive to negative.
Remember, it's defined by a small positive test charge, therefore the electric field is going to go from positive to negative. If you think about it, if we take a small positive test charge, we place it in the electric field, it's going to be repelled from the positively charged plate and attracted to the negatively charged plate. It's going all the way back to the law of charges. Michael, do you have a question? Say again? I know, but when we're talking about defining the electric field, it's always defined by a small positive test charge, right? So what we were talking about here was just what's the direction of the electric field and where are the positive and negative plates. So now we're going to put in a negatively charged object and see what happens. Okay. So now, if this negatively charged particle is traveling this way, when it goes through, it's going to feel a force. Meg, what is the direction of that force? As it's going through the electric field here. It's not going to feel a force in that direction. You can tell me the direction of the force on the negatively charged objects. Bless you, Sierra.
Wouldn't it be towards the positive?
It's going to be toward the positive plate. It's opposite the direction of the electric field. So when it's in here, when the negatively charged object is in here, the electric force is going to actually be down, opposite the direction from the electric field. Jenkins.
Wouldn't it be like diagonally towards the center of the two plates? Or?
The electric field between two positively charged plates is actually a constant electric field. Therefore, the force is going to be in the opposite direction from the electric field, which is going to be straight down. You're thinking of the direction of the motion of the object, right? Because the object, which experiences a force down here, is going to go and follow a parabola that looks like this, right? So if the length of between the two plates is equal to, if we know that length is equal to 25 centimeters, the question is, what is the velocity final of this electron? Okay, so let's start out by drawing a free body diagram of all the forces acting on the electron. Free body diagram of all the forces acting on the electron. Please, Bill.
Force of gravity down.
Force of gravity down, and
Force electric down.
force electric down. Okay. So let's take a moment and talk about the electric force versus the force of gravity. Okay. The electric force divided by the force of gravity. The equation for the electric force in this particular case is going to be equal to what, Stacey? KQ over R squared is the equation for an electric field of a point particle, but this is the force acting on a point particle, which are two different things. Nick? It's just going to be Q times the electric field. Q times E. The force of gravity is M times G. What is the charge of an electron? Nitich.
1.60 times 10 to the negative 19.
Good, 1.60 times 10 to the negative 19. You realize you need to know, or I'll rephrase that, it would be very helpful for you to know the charges on a proton and electron, which you should know are the same, opposite in magnitude, and the masses of a proton and electron. They are on your table of information, so you could definitely have those if you need them, but they are going to be so commonly used that it's very helpful if you know them. So we have 1.6 times 10 to the negative 19 times the electric field, which is 25, divided by the mass of the electron, which is on your table of information so that you can find it and you can realize that that is something helpful for you to know. Which is what, Jenkins, did you get it? Who's got it? 1.67 times 10 to the negative 27 is not the mass of an electron. That is the mass class of a proton. So that is the mass of a proton. The mass of an electron. Jenkins, try again.
9.11 times 10 to the negative 30.
Again, you don't have to have it memorized, but it's very helpful if you do. Times G, which here on planet Earth is 9.8. So the electric force divided by the force of gravity is equal to what number, please?
5 times 13.
I believe it works out to be 4.48, right? Times 10 to the what?
13.
That's not what I got. Did I get it wrong?
Hold on. Wait. 11.
Times 10 to the 11th. In other words, the electric force is 4.48 times 10 to the 11th times the force of gravity. In other words, the electric force is equal to 4, 4, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9 times the force of gravity. 1, 2, 3, well, let's see, this is 1,000, million, billion, 448 billion times greater than the force of gravity. This makes the force of gravity a three-syllable word, four-syllable word, negligible. Okay. So the force of gravity is negligible for atomic particles. For non-atomic particles, in general, it is not negligible. For example, something on the order of a milligram or a microgram, it's not going to be negligible. So we try to not have anything like between those. So you're either going to be dealing with something that's very close to an atomic particle or something that's on the order of a milligram or something like that. What was that? Did that answer your question?
No.
Okay, go ahead.
I was wondering, for a free body diagram, do you still bring in gravity or no?
So I would not, in this case, even put the force of gravity in the free body diagram, right? Because it's negligible, and we know that's true for all atomic particles.
Because it's moving so fast, it doesn't weigh anything.
No, it actually has nothing to do with whether it's moving fast or not. Even if it were at rest, this has nothing to do with how fast it's moving.
Just because.
By virtue of the fact that the force of gravity is 448 billion times less. Okay. Yes. All right, so we've got all of that. We just need to figure out how, what are we trying to find? Velocity final. So help me figure out the velocity final. Tim, what are we doing next?
Sorry.
Tim, you're right up there. Oh, you can't see him? Maybe you should switch when we go over to that side. You can go over there. It wouldn't bother. And you wouldn't be bothered by it.
No, it's cool.
Sorry. All right, so we need to figure out velocity final. Thoughts, Hillary?
Find the acceleration.
Find the,
Acceleration.
okay, how do we do that?
From the forces.
Pick a direction,
In the wider.
keep going,
Equals
equals
FE.
FE, positive or negative?
Negative.
Negative, which equals
MAY.
MAY, May.
MA sub Y.
How about mass times acceleration in the y direction? The more often that you actually use the names of them, the better off you are in the long run. Mass times the acceleration in the y direction. So we have negative QE equals the mass times the acceleration in the y direction. The acceleration in the y direction is equal to the negative times the charge times the electric field divided by the mass, where charge is 1.60 times 10 to the negative 19. The electric field is 25 divided by the mass of the electron, 9.11 times 10 to the negative 31st. The acceleration in the y direction, please. Oh, heck. Let's not do it that way. Let's do it with variables. Much more fun. The acceleration in the y direction. So now we have the acceleration in the y direction is clearly equal to a number, so we can use what class? UAM. We have a UAM equation. Let's see. We know velocity initial in the y direction. We're looking for velocity final. We know, no, we don't. What do we need to do before we can figure out the final velocity here? Picked.
We know the velocity in the x direction is constant,
Therefore,
so velocity equals the change in position.
velocity in the x direction equals displacement in the x direction over delta t. We need to solve for delta t. This is just like projectile motion. Delta x over the velocity in the x direction. Delta x is 0.25. The velocity in the x direction, I believe, is 1.0 times 10 to the 6th meters per second. So delta t is equal to
2.5 times 10 to the negative 7.
times 10 to the negative 7 seconds. Just for fun, that's 250 what?
Micros.
Nope. Nanoseconds.
Oh, 220.
Sorry, you just got to know those. So we can then use the acceleration in the y direction. We can use velocity final in the y direction squared equals velocity. No, we want to use velocity final in the y direction equals velocity initial in the y direction plus the acceleration in the y direction times delta t. Velocity initial is 0. Acceleration in the y direction equals negative qe divided by the mass times delta t. I suppose we could have left all variables in there. That would have been more fun. Velocity final in the y direction equals negative q 1.6 times 10 to the negative 19 times e, which is 25, times the change in time, which we just got to be 2.5 times 10 to the negative 7 divided by the mass 9.11 times 10 to the negative 30. What do we get?
You already know.
Yeah. I like to get help though. I don't want to be here by myself doing stuff. So. Thanks, Dave.
-7.194 times 10 to the negative 61.
Negative.
61.
Just it's Believe it or not, using your calculator is a useful skill for this class. This is the time for you to practice, Zach.
1.098
1.098 times 10 to the 6, independent confirmation.
Yeah, so
Yeah.
Oh my god. Oh, there it is. There's my mistake. I made a small mistake. I apologize. It's right there. It'll be okay. So the velocity final in the y direction, meters per second. I'll fix that in the future. So the velocity final is equal to 1.00I minus 1.10 J times 10 to the 6th meters per second. So ends chapter 23.